As a quick example of the divergence test, let's look at this infinite series. Totally makes sense to plug in all these numbers k into this formula. 0, 1, 2, 3, 4, build that infinite sum, look at the partial sums. Again, if you wanted to be really careful, you'd note that this is, by definition, the sum, the limit, sorry, of the partial sums. Like this. And then we could ask, does this limit converge? In other words, does the series converge? And you might be pretty happy about this and pretty optimistic, because this is exactly the kind of thing we can calculate the limit of. We can take the limit as k goes to infinity of this rational function. This is an example where you can use our methods from real numbers, so it's the same. Or if, let's say, if the limit exists when we make it in x's and we put in even more numbers, all the real numbers, if this limit exists, then the limit of these terms exists. Okay, and that, let me just do it kind of quickly, we can multiply by 1 over x cubed over 1 over x times 1 over x squared. It's the same thing, that's just 1. And the reason I separated it out is it just makes it easier to see what's going to happen. 7 over x cubed. 1 over x conveniently multiplies this guy. Aha. 1 over x squared. Oh, that's nice. Okay, so it's the usual thing of looking at a rational function, and and what do you get? You get 1. So that limit exists. And the quick and dirty way, of course, is to cover up all the lower order terms. And that works as long as there's no weird square roots, no weird sign issues. If it's really a pure rational function, cover up that, and the 1 and the 9, it's x cubed over x cubed, and it goes to 1. So here's the thing, though. Be careful. We've said that the terms get closer and closer to 1. So eventually, it's like adding 1 plus 1 plus 1 plus 1 plus 1 to a really high accuracy. That means that the series diverges. So unfortunately, even though we have something nice to say about the limit of the terms, it's just crazy to try to add them up. There's very little meaning we can make about adding these things up. So the series diverges by the divergence test because, yes, we were able to find the limit of the terms, right? This is a sub k. We were able to find the terms, the limit of those, and it was going to 1, and that's not 0. These are not even trying to get small. It's not even funny. So that's an explicit example, a little more complicated than the ones I showed before, of using the divergence test. So as always with this kind of thing, one of the things we want to do is build a stock of examples. And I'll mention the harmonic series. Again, I didn't show that myself, but it's just, there's lots of good expositions of that. Okay, this diverges. It's everybody's favorite example of a series whose terms do go to 0. You can't show that it's divergent by the divergence test, but it diverges nonetheless. Okay, that's the harmonic series. Okay, and I've mentioned already a special case, or I've mentioned it a couple times, and that's the geometric series. So the 1 plus 1/2 plus 1/4 plus 1/8 was an example of that. So let R be a fixed real number. Oh, and A, actually, R and A be fixed real numbers. It looks like Rob A or something like that. A and B be real. A and R, just kidding. Okay. And so we're going to take A plus AR plus AR squared plus AR cubed plus, and we're going to try to take that out to infinity. Does that converge? Okay. And different books do this in different ways, but to match up with the power series stuff, I want to call this term number 0 because that's really AR to the 0, and this is AR to the 1. So this is term 1, term 2. So it starts with term 0. So in other words, we're going to write it as sum k equals 0 to infinity of a r to the k. You'll often see it starting at 1 and a k minus 1 here. But when you're doing power series, that's just unnecessary. Okay. So does this converge? Well, it's going to depend on what R is. And not too surprisingly, when R is big, this is a bad idea. When R is small, this is a good idea. And let's be a little careful about that. This is, again, something that's in every book, but I think I might as well spend the time. What we have, let's see, the nth partial sum here is A plus AR plus AR squared, and then you stop at AR to the n. And so the key is to get a shortcut, a very different way of writing that formula. And there's various ways to derive it, but the usual way is I do a clever little trick. I multiply that by R, and the A becomes AR. And the AR becomes AR squared, but I'm moving them over in terms of where I write them. And the AR to the n becomes AR to the n plus 1. And you know what? There's hiding in here, let me just write it, there's an AR to the n minus 1 there, which becomes an AR to the n. And everything else fills in and matches exactly. So if I subtract this, lots of cancellations happen. It's a very, very good technique of looking at two quantities and trying to play them off against each other with a cancellation in mind. So you get S sub n times the quantity 1 minus R. The A doesn't have a partner, but all these guys have partners. And this one doesn't have a partner. And so you get 1, and then notice there's an overall minus sign, R to the n plus 1. And so this is a very famous result. The sum of the finites, the partial sum, this is nothing about limits yet, but it allows us to take the limit in a much more rigorous way than we would otherwise. So this is just a really important thing. This is sum of a finite geometric sequence. We're not going to use the word series here because I like to use series for where we really are going to infinity. And so if you stop at a particular n, this is a really, really nice formula to have. And the great thing now is that the limit is pretty clear. This is a constant. 1 minus r is a constant. 1 is a constant. If I take the limit of this guy, as n goes to infinity, of Sn, it's a over 1 minus r. That's a constant. That's always going to come out. Times the limit is n goes to infinity, 1 minus r to the n plus 1. And the only issue is, what does this do? And this is just powers of a number. This converges if r is between minus 1 and 1, if the absolute value of r is less than 1, because then I'm taking higher and higher powers of a small number. If not, then I'm either going to get big numbers, like 2 to the n plus 1 diverges, or if it's 1 or minus 1, if it's r equals 1, this doesn't make any sense at all, so that's a problem. And if r equals minus 1, it just oscillates. So it's exactly when r is small. So for example, the one I was showing before was r equals 1/2 and a equals 1. Okay. And not only that, when it converges, we know what this thing goes to. It's not going to some mystery limit. This goes to 0, and so the whole thing is a over 1 minus r. So that's the summary for the geometric series. Let's write that out. If r is between minus 1 and 1, not inclusive, then the sum, the infinite sum of a r to the k, is equal to a over 1 minus r. And if not, then this sum diverges. Okay, that's a big deal. The geometric series is the heart of so much in this this whole subject. So the harmonic series was an example of something that's guaranteed to be bad. It diverges. The geometric series sometimes is good, sometimes is bad. We're maybe a little more often interested in the good side when we're summing up something where the terms actually get small. And again, an informal way to say this is that when the terms get small geometrically, like if I have 10 times, or 10, let's say, plus 10 thirds plus 10 ninths plus 10 27ths plus 10 81sts, here r is 1/3. It's the ratio between any term and the next. that's less than 1, I can put the dot dot dots on there and it's going to converge, and I'm even going to be able to tell you what it converges to. Here a equals 10, and so the sum is going to be 10 over 1 minus 1/3, 10 over 2/3, or 10 times 3/2 is 15. That's pretty cool. That if I extend this further and further and further, I'm going to get a bunch of finite sums that get closer and closer to 15, and as close as I want to 15. So let me show you. Yeah, I don't think it'll be too long. Let me give you a taste of something in our book is a couple of sections ahead, but I feel like you get more of a sense of why it's important to have these special examples if you show why that tells you something about other series. Just a very brief mention of the comparison test. It's another aspect of our slogan, just another way to make our slogan precise. If the terms of a series go to 0 fast enough, the sum, the series itself, should converge. Now, there's some issues with signs that it's helpful to just say, suppose you just have positive terms, and I'm not trying to let things converge in terms of like wiggling or cancellation. So suppose like a sub n and b sub n are all greater than or equal to 0. Okay. Then, if, let's say the a sub n's are all smaller than the b sub n's, and the sum of the b sub n's does converge. I guess I switched to n. I usually like k for this purpose, but okay, it's okay. N is also very standard. Okay, so I'm going to say this informally in this video. This is saying that the b sub n's go to 0 fast enough so that they converge. And everything's positive, so it's easy to compare sizes. And the a sub n's are smaller than the things that are going to 0 fast enough. Well, I think, and this is absolutely true, then the sum of the a sub n's converge to. Okay. So it's important that this guy was, because these guys are positive, that's the crucial thing. These weren't going to 0 because it's like a bunch of big positive and negatives sort of canceling out really magically. That would be a sort of trickier way to converge. But if everything's positive terms or non-negative terms, then the reason this converges is basically these are going to 0. The terms are going to 0 fast enough. These guys are better than good, so this is good. This is very, very analogous to a comparison test we had for improper integrals. Okay, so real quick example to finish it off before I get too long. For example, suppose, or maybe a couple examples if I think we can deserve the time. Suppose I have, I'm going to go back to k. Because I like using k for the dummy variable, so in case I ever need to use Sn, I have n available for that. But it's not a big deal. The letters don't fundamentally matter. Okay. All right, let's look at this. It's a moderately complicated formula for the summation. But what we can notice is that the 3k plus 1 on the bottom, that only ever makes this smaller than 2 to the k over 3 to the k. So if this is a to the a sub k, the terms, notice I'm picking out just the terms, each term is definitely less or greater than or equal to 0, it's positive, and they're less than the quantity 2/3 to the k. Aha. And I know that the sum of 2/3 to the k, that's a geometric series, that converges. Therefore, this converges too. Now notice what happens. It didn't really make a comparison between the summation and the summation. The comparison happens on the term level, and then you can say just that this converges because this converges. If the terms compare and the sort of the simpler one converges when you sum them, then the sum of this one's going to converge as well. So that's a good example of that. Let me just show you 2 more examples real quick. How about the sum k equals, I'm going to go from 1 to infinity, you'll see why in a second, ln k over k, natural log, or sometimes just log. I couldn't go from 0 because log of 0 isn't defined. Okay, and 1 over k, and 1 over 0 isn't defined. But, yeah, no, this works. Okay. So let's see, does this converge? Okay, well, this is really using the flip side of the convergence of the comparison test. If you're better than good, you're good. But if you're worse than bad, you are bad. So this is really logically equivalent to what we said before, but I'll say it explicitly. If a sub k is bigger than b sub k, and the sum of b sub k diverges, then the sum of a sub k also diverges. Because if it converged, then we could just flip the roles and say, oh, the b sub k's are smaller, and if a sub k is good when you sum them, then the b sub k should have been good. But we know the b sub k's are bad. So it's just, what's called the contrapositive of the original statement. So better than good is good, and worse than bad is bad. Okay, now wait a minute. As soon as k is bigger than 1, these guys are bigger. As soon as k is bigger than e, let's say, these guys are bigger than 1. And so that's this. Actually, I might as well mention that. The comparison test works as long as this kind of comparison eventually works for all k big enough. If you have a few counterexamples for finite, it doesn't matter because all we're worried about is the limit. It goes to infinity. So as soon as k here is bigger than, it's 3 or more, these guys are bigger than 1. So eventually, ln k over k is bigger than equal to 1 over k, and I know that the sum of 1 over k diverges. That's the famous harmonic series. So therefore, this diverges. Ah, man, that's too bad, but that's life. Now, last little thing. I know it's getting long. What if I put it here? Okay. All right, well, now the ln k factor is helping me, but here's the thing. The natural thing to compare it to in our small stock of examples that we know anything about is 1 over k. Yes, this is making it better. It's making the term smaller. So this is a better series than the harmonic, but the harmonic is known to be bad. So something better than bad, we really don't know. So this is where we would need a more finicky test. And that's the kind of thing you actually get from what's called the integral test.